Section 7.1, the law of sines. An oblique triangle is a triangle that does not contain a right angle. It can have either 3 acute angles or 2 acute angles and 1 obtuse angle. The term oblique triangle comes from the Latin word which means slanting or sideways. The trigonometric relationships that are used for the sides and angles of right triangles are not applicable to oblique triangles. We used right triangle trig to solve a problem like this. We'll need a different approach to solve a problem like this. For oblique triangles, we'll investigate and implement alternative relationships among their sides and angles. The law of sines is a relationship amongst the sides and angles of any triangle. The ratio of the length of a side of a triangle to the sine of the angle opposite that side is always the same for all 3 sides of the triangle. Solving a triangle means finding all its sides and all its angles. The law of sines can be used to solve a triangle in which we know one side and 2 angles. These 3 measurements can be abbreviated with ASA if you know 2 angles and the side between them, or SAA if you know the 2 angles and a side not between them. Here's a procedure for solving triangles of either of these types. Because we know 2 angles, we can find the third using the fact that the 3 angles of a triangle always add to 180. We'll then use the law of sines to find an unknown side, and then we'll repeat the law of sines to find the last side. Even though these 2 cases are presented as distinct, they're really the same, so we'll use the identical method to solve either one. Let's look at this example. Here we have a triangle where we know angle A, angle C, and side C. Since we know 2 angles, we can find the third because the 3 angles have to add to 180. So angle B is 34 degrees. Here's an algebra alternative. Notice on the left, we solved for B first and then substituted. On the right, we substituted first and then solved. You can use either method you prefer. Now that we found angle B, we can use the law of sines to find a side. We'll set it up with a pair that we know both the angle and its opposite side, which is angle C and side C. We can start with A. We have A over the sine of 64 degrees. We cross multiply, divide both sides by the sine of 82, and then we use our calculator to approximate side A. And then we can label our triangle. Before moving on, I want to show an alternative algebraic approach. We are going to still find side A again, but this time we're going to cross multiply and divide by the sine of C before substituting in our values. And now we'll substitute in the values and use our calculator, and you'll see we get the same answer. Here are the 2 approaches side by side. On the left, we substituted the values first and then solved for A. On the right, we did the algebraic manipulations and then substituted. Use whichever you prefer. Here's a quick recap before moving on. We began by finding angle B, then we used the law of sines to find side A, and now we need to find side B using the law of sines. Once again, we'll use the fact that we know C, and we set that equal to the unknown side B over the sine of angle B. We cross multiply, divide by the sine of 82, and we use our calculator. This gives us a value of 7.9, and we've completed solving this triangle because we found all the unknown sides and angles. In example 2, we're given angle A, angle C, and side B. So once again, with knowing 2 angles, we'll start by finding the third angle. That gives us a B value of 117.5, so we label our triangle. And now we'll move on to finding a side by using the law of sines. Since we know side B and angle B, we can use that to find side A. We cross multiply, divide by the sine of B, and then substitute in our values and use the calculator. This gives us 8.7, and now we'll move on and find side C. We set up the law of sines, cross multiply, divide by the sine of B, substitute in, and use our calculator, and that gives us the last side of side C is equal to 5.2. And we now know all the sides and angles of this triangle. Sometimes we're asked to solve a triangle where we know 2 sides and the opposite angle of one of those sides. This case is abbreviated as SSA and is known as the ambiguous case. It's ambiguous because it can lead to one triangle, two triangles, or no triangle at all. We can visualize these with these diagrams. If we look at no triangle, that occurs if side A is too small to reach all the way down. We get a right triangle if A is exactly the height, and so it just barely touches. We would get two triangles if A is just slightly bigger than the height, so you could lean it in for one triangle, and you could lean it out away from side B for the other triangle. And then finally, if side A is bigger than side B, you can't lean it in towards B. The only option we would have is to lean it out. The good news is you don't have to think through all these diagrams when you're doing the problem. The law of sines will determine the number of triangles, and the algebraic process will reveal all the possible outcomes. Any possible outcomes will be determined by the sine of B. If the sine of B is greater than 1 or less than -1, that's impossible, so no triangle will be formed. Recall the graph of the sine oscillates to a maximum height of 1 and to a minimum of -1. Furthermore, if the sine of B is between -1 and 1, that's a legal value for the sine, so that will lead to either one triangle or two triangles. Based on the value of the sine of B, this will be the procedure that we follow. We'll know that we have no triangle if the sine of B is an invalid value. So if we get a value that is greater than 1, we can stop right away and answer that there's no solution. We will be in a situation where there's one or two triangles if the sine of B is a valid value. We'll then calculate angle B and find its supplement. Remember, supplementary angles are two angles that add to 180, and so we'll find B sub 2 by taking 180 degrees minus B. For the first triangle, we'll use angle B. Because we'll then have angle A and angle B, we can find angle C. We can calculate side C using the law of sines, and then we move on to seeing if we have a second triangle. For that, we have to look carefully at B sub 2. Remember that if our first two angles add up to 180 or more, there won't be any degrees left over for the third angle. So as it says here, we find the sum of angle A and the supplement of B to see if they're less than 180. If so, a second triangle exists. We then can calculate the third angle, and then we find the remaining side. When the ambiguous case leads to two valid triangles, we use subscripts of 1 for the values of the first triangle and subscripts of 2 for the values of the second triangle. In example 4, we have two sides and the angle opposite one of those sides. Because we only have one angle, we can't use the technique of starting by finding all the angles, so we'll use the law of sines. We set up the values that we know, and we can solve this for the sine of B. We cross multiply and divide by the coefficient, and we have sine of B isolated. We use our calculator, and at this point we notice that 1.53 is not a valid value. If the sine of B is greater than 1, then no valid angle B exists, and therefore no triangle can be formed. There is no angle B for which the sine is greater than 1, and there is no triangle with these given measurements. Here's the way it looks graphically. You're not obligated to make a sketch, but this is approximately the situation that we're in. So the answer is that there's no triangle with these measurements. In example 5, once again, we have a triangle where we know two sides and the angle across from one of those sides. So we'll use the law of sines. We substitute in the values we know, cross multiply, divide both sides by the coefficient of the sine of B. Then we use our calculator to make that approximation. And we recognize that the sine of B here has a valid value of between -1 and 1, and therefore we'll end up with one triangle or two triangles. We find angle B by using the inverse sine feature on our calculator. That gives us a 50-degree angle. And in addition to that, we know that any particular sine, such as 0.7648, will give us two angles between 0 and 180. The other one will be the supplement of B. To find the supplement of B, we subtract it from 180. We'll call that B sub 2. B sub 2 is 130 degrees. We need to determine if that 130 degrees is a valid angle in this triangle. To do that, we look at angle A and angle B sub 2 to see if their sum is less than 180. If not, there won't be any degrees left over for the third angle. So A plus B sub 2 simplifies to 165. That's less than 180, and so there's two possible solutions. We'll use b sub 1 equals 50 to complete our first triangle, and we'll use b sub 2 equals 130 degrees to complete the second triangle. We'll work on these two triangles side by side. So for triangle 1, we can substitute in 35 degrees for A and 50 degrees for B1, and that'll allow us to solve for C1, which is 95 degrees. For B2, we substitute 35 in for A, 130 in for B2, and that allows us to find that C2 is 15 degrees. Now we take these values and we use those to find the last side for each triangle. That involves the law of sines. We substitute in the values we know, cross multiply, divide by the sine of 35, and then we use our calculator. For triangle 2, we use the law of sines, substitute in, do the algebra, and then compute it on our calculator, and we get C2 is 5.4. So let's take a look at the procedure we used for this problem. For triangle 1, we had the given information. It's the same for triangle 2. We then started with the sine of angle B, and we saw that it was a valid value. So we took the inverse sine to see that the angle was 50 degrees. For triangle 2, we took the supplement of that angle. 180 minus 50 is 130. And then when we knew two angles of a triangle, we can find the third. So we did that for both triangles. Then finally, we could find side C1 by using the law of sines, and side C2 the same way. And this gave us a full solution for this problem.